Okay, so let me also thank Antonio, Augusto, Tomo for this nice conference. So I'd like to talk about the superconductivity in single and multi-band Hubbard models. And my question is, can we actually optimize them, in my own view? Okay. This is the strategies for higher TC, first optimizations. And let me first talk about computational method. And then I come down to single against multi-band cases and single against multi-orbital cases. And I'm going to stress that multi-band systems should not be confused with multi-orbital systems. They are very, very different. Okay, and as a prominent example of the multi-band system, then I'll talk about flat band superconductivity. Sorry, yes, the multi-orbital systems should not be confused with multi-band systems. And as a prominent example of this one, I talk about flat band superconductivity, where we have flat band on top of the dispersive band. And I talk about the pair scattering processes on this. And then finally, I'll touch upon some collective modes in superconductors. Okay, so let's start with this computational method. There are many, many theoretical methods to treat strongly correlated systems. One typical example is a dynamical mean field theory, one of the few methods that can deal with Mott transition. So that's nice. But this is a kind of mean field theory. Another method is called FLEX, fluctuation exchange approximation. This can treat spin fluctuation mediated D-wave pairing. That's nice, but this method cannot treat Mott transition. So one idea is, why don't we combine DMFT with FLEX with this kind of double self-consistent loop? And Kitatani considered that. And he called this DMFT plus FLEX method. And the obtained TC dome against a band filling, this is a half filling point, and I'm holding in that direction. We've got a nice TC dome with this FLEX plus DMFT. And the physical reason is, as you approach the half filling, you increase the pairing interaction, but you are increasing the self-energy, which will suppress TC. So dome is the outcome of these two opposite tendencies. So that's nice, but in the DMFT plus FLEX, vertex corrections are still neglected. What is a vertex correction? So if you look at this kind of four-legged vertex, which is usually called gamma, and usually we consider a Feynman diagram something like this in RPA FLEX TPSC. So this line may be a thick line, a renormalized line, but anyway, this is a kind of a boson exchange diagrams. But there are a host of other diagrams, and that is called vertex corrections. And if you have a strongly correlated system, it well may be that this plays an important role. Okay, and if the vertex correction is at work for superconductivity, then we are talking of going beyond this type of boson exchange mechanism. And some works already talk about non-bosonic glues or hidden fermions, as we heard from Imada-san on Monday. Okay. The method we take here is the dynamical vertex approximation are usually called D gamma A. This was originally devised by Carsten Held in Vienna. For this four-legged diagram, we can classify that into fully irreducible vertex, particle hole channel, particle hole reducible channel, transverse particle hole reducible channel, and particle-particle reducible channel. It's a bit of a tongue twister. But DMFT corresponds to the one particle irreducible vertex, while this D gamma A corresponds to two particle level non-local vertex. Okay. Carlsten introduced this for the normal states, and recently we have extended that to treat superconductivity. Okay. And the paper, which is on the archive, has some strange title. Why TC is so low in high TC cuprates? Importance of the dynamical vertex structure. So, as Tomo stressed in his talk, we've got a 2-order magnitude reduction from the original electronic energy into the superconductivity TC. So the big question is, why this 2-order magnitude reduction? Can we theoretically trace that back? And this is a D gamma A result for lambda is a L-Hirschberg equation eigenvalue, a measure of TC, and this is a band filling. Again, this is a half-field point. And again, we've got TC dome, and that is again due to pairing interaction increasing in that direction, while the self-energy correction also destroys the pairing. So D gamma A also has, well, D gamma A has a TC lower than in DM flex, but TC dome is again reproduced. Okay, one interesting point is pairing interaction in this D gamma A, even for the on-site Hubbard model, is very, very frequency dependent. So this is the L-Hirschberg equation, and this is an essential effective pairing interaction, gamma, like this. So two electrons with frequency omega and minus omega enters and go out with omega prime and minus omega prime. And in usual axonic patients, if you look at this pairing interaction, that depends only on the difference between omega and omega prime, like this. But if you look at the D gamma A result, we have a very strong frequency dependence around here, around Fermi energy. Okay, so if you take into account the vertex correction, the pairing interaction becomes very omega dependent. Okay, we can go in further detail by looking at this structure for the vertex in the magnetic channel. I call this a local vertex correction, which has two arguments, Matsubara frequency nu n and another Matsubara nu n prime. And I plot the vertex correction against n and n prime, very much frequency dependent. And we can even resolve that into step-by-step inclusion of interaction. So this is a Bayer-U result. This is a second-order result. And this is a third-order result. And if you look at the L-Hirschberg lambda, this is the correct answer. In the Bayer-U, lambda becomes very much larger. Then in the second order, this goes back almost to the correct value, and then some correction. Okay? So the question is, what causes this main reduction from this Bayer-U to the second order vertex process? Okay. Usually we consider magnetic pairing interaction, which consists of particle or channel propagators. But if you take account of the vertex corrections, particle-particle channel also enters. And the conclusion here is this one has a very significant contribution and a main reason why TC is so low. Okay? And this is also a reason why we've got a very strong frequency dependence. Okay? So the bottom line is the vertex correction suppresses TC, and the question is there any way out? One possibility is to have off-site extended Hubbard type interactions, which will make this kind of frequency-dependent interactions, as suggested by dual boson theory or extended DMFT approaches. Okay, another possibility is to manipulate band structure designing, including multiband models. So let's move on to the multiband systems. Okay, so I come to here. So everyone knows that Q-plates are basically single orbital, single band system. Ion-based superconductor is a multi-orbital, multi-band system like this. But even for the Q-plates, we can show that there is a second orbital which has to be considered for the full understanding. So for instance, this is the experimental compilation of experimental TC against some parameter R, which is if you go to the right, you increase single band character. If you go to the left, then you have better nesting. Okay, this is our theoretical result. And so among these two opposite effects, the bottom line is the effect of one band character is bigger than the effect of nesting. So make your system as much as one band character. Okay, ion-based superconductivity has obviously multi-orbital system with these different d orbitals. And in that case, multiple nesting vector, such as these, can work either constructively as in these compounds with very nice multiple nesting vectors ending up with S plus minus pairing, while in other cases, these nesting vectors can be frustrated. Then we can end up with low TC nodal S or low TC nodal D. Okay, so this is a complication in the multiband case. But we can summarize these in this table. So one band case, multiband case, merits, and demerits. And in the one band case, we can optimize swing fractions mediated anisotropic superconductivity. In multiband cases, can accommodate sign reversing full gap pockets as in the S plus minus ion superconductivity. And this can also accompany incipient bands, as in ladder systems, and can accommodate flat band superconductivity. Okay, so what are these? What are incipient bands and what are the flat band superconductivity? So let me explain. Okay, to start with, I said ion-based has multi-orbital and multi-band structures. So this is the Fermi pockets. And if you walk along a Fermi pocket, then your orbital character changes from dx squared minus squared to dyz, something like that. And the point is only the nesting between the same orbital character mediate pairing. So these are the only relevant pairing vectors. Okay. And in that kind of physics, multi-band systems should not be confused with multi-orbital systems because single orbital systems can be multi-band depending on what structures, typically as in non-Bravais lattices. Okay, so for the multi-orbital cases, as in Q-plates, so I display these different orbital characters with different colors. This is not favorable. And if you increase a single band character like this, then this will enhance your TC. Okay, this is a multi-orbital case. For a multi-band case, you can have multi-band, multi-orbital situation, but much better situation is multi-band, single orbital case. So single orbital character, but more than one band. And this is drastically favorable for superconductivity. Okay. So in one band system, when multi-orbitals are involved, opt for one band like this. For multiband cases, when a single orbital multiband is realized, then opt for multiband. And in this case, the second here should be put closer to the Fermi energy. So let me explain that. Material design example exists in that line of approach. Yes, this is one example. This is a recent work on the hidden ladder in little less than copper bilayer 3 to 7 compounds. The actual proposed material is strontium-3, molybdenum-2, oxygen-7. If you look at the lattice structure in black, this just looks like a double layer system, nothing else. But if you put d orbitals on that lattice with dxz orbital like this, we've got a two-leg ladder like this. And for the dyz orbital, we've got a two-leg ladder like this. So that's why we call this system hidden ladder. And if you calculate the band structure, then Eliashberg lambda is very, very high, similar to mercury copper oxide with Tc 90 Kelvin. Okay, but there's even more interesting model, which is a flat band superconductivity. So let me explain that. Okay, the flat band model theoretically has been around from back in the 1980s or 90s. So if you have a right lattice structure, then you've got a dispersionless band in your band structure, okay? And this was conceived to have ferromagnetism. So if your Fermi energy is right at the flat band, then your ground state is ferromagnetic. But today we are interested in superconductivity, so let's move away from the flat band. Then the question is, can you have enhanced superconductivity? Okay, and these flat band models contain more than one atoms per unit cell. Then flat bands are necessarily multiband systems. So this is a single band multiband, single orbital multiband system, which I said should be an ideal situation. Okay, then what do we know about multiband superconductivities in general? Back in the 1950s, there's a famous Soule-Kondo mechanisms. If there are two bands and if there are hybridization between these two bands, then this will enhance, always enhance Tc. Here we are talking about the double band with same orbital character where the second band is flat. And in this situation, I'm going to show that this flat band can be very highly entangled, even topological. In that case, the question is, what should the pairing interaction look like? Okay, so this is a simplest possible flat band, quasi-1D flat band model, which is called diamond chain. These are lattice sites, and the band structure has 3 bands, dispersive ones and flat band. And there's a related proposal for the cross-linked two-leg ladder by Kuroki and the company. They also considered the case in which the second band is flat, and their conclusion is, yes, in this situation, we have very high Tc. And the basic idea is this. Okay, the Cooper pair is basically formed on this dispersive band, and why this flat band is completely empty, we can still have the quantum mechanical Cooper pair scattering as intermediate states. And since this is a flat, there's a many channels for this virtual quantum mechanical pair hopping. Okay, and okay, there are some suggestions that this system actually contains a very large RBB, and some suggestions that this is approximately realizing some mineral. Okay, let's move on to the DMRG result of ours. We calculated pair-pair creasing function. This particular pairing is the most dominant pair. If you look at the pair-pair correlation, we have a very long-tailed pair-pair correlation. So enhanced pair correlation around 1/3 filling, which is the lowest band almost fully filled, flat band completely empty, peaked around Hubbard U around 4. And one interesting observation is we used DMRG, a renormalization group method, and usually we can just take 100 or 200 states to retain. But in this case, unusually large, something like 1,500 states are required in the DMRG calculation. Namely, we have an anomalously large entanglement. Okay, so this is a phase diagram. This is a band filling. This is a 1/3 filling. And just below that, we have a superconductivity with anomalously large entanglement. And exactly at 1/3 filling, namely dispersive band completely filled, flat band just empty, then we can show that we have a topological insulator. How we do know that? For that, we can calculate entanglement spectra and edge states. I'm not going into detail, but the essential point is these quantities very much depend on how you cut your system to calculate entanglement spectra and edge states. And this very much reminds us of the famous Duncan Haldane's model for the spin 1 anti-Hubbard chain, in which also there is a very much difference between the case in which you cut your system here or here. And indeed, these two belong to the same topological universality class. And flat band superconductivity, well, you might think that that might be an accident for this diamond chain, but that's not the case. We can consider various other systems, and this is the distance of the chemical potential from the flat band. And you have an enhanced TC, and just in the vicinity of the flat band, superconductivity vanishes. So the message is, okay, you have a flat band, not right at, but close to the chemical potential. Okay, in more general terms, this may be considered as incipient bands. For instance, in iron-based superconductivity, such as iron selenide, people talk about the incipient band, which is below the Fermi energy, no Fermi pocket for this one, but still, this is very much at work for the iron-based superconductivity. But originally, the concept of incipient bands are introduced by the Kuroki and the company's paper I just introduced. Okay, another big question is well, I showed that the flat band in my system is topological. So the big question is, when you have that situation with that favor superconductivity, and Päivi Terma in Finland and the company has this theoretical work, their claim is if you have a topological flat band, your superfluid weight is lower bounded by the topological number of your flat band. So this is something like a topologically protected superfluid weight. And this is obviously very interesting. And they show that for the attractive Hubbard model. So the more interesting is what will happen to the repulsive Hubbard model with anisotropic pairings. Okay, Päivi Terma has another paper for this kind of a leap lattice, again for the attractive Hubbard model. So the question is what happens to the repulsive model. Leap model this. This has a Dirac cone and a flat band. And since we've got a two-dimensional system, density of states vanishes here. So this is not good. And another question is, can you have a quadratic band penetrated by flat band? Is that possible? And recently we showed that that is possible. So this might be a good system to look for. I'm over. How many? 1 minute. Okay. This morning, we heard about a twisted binary graphene from Pablo, and he talked about this kind of flat band. And for me, this very much looks like this system here. And in the phase diagram, if you make the vertical axis energy, then we've got this superconducting dome, which tells you that you should be close to, but not right at the flat band. So this is an interesting possibility to apply this kind of idea to Pablo's system. Okay, since time is consumed, let me skip the part about corrective excitation. The bottom line is the bottom line is can collecting modes affect superconductivity itself? Usually collecting modes are excitation modes, but can they affect superconductivity in equilibrium itself? And there are some theoretical suggestions that they do with this kind of Leggett mode propagators. And D gamma A I introduced today can deal with that if you take parquet diagrams, this kind of diagrams. Okay, so let me summarize. I talk about optimization, flat band superconductivity, and as future problems, I didn't actually show that in these flat band superconductivity and so on, we have a significant vertex correction. So this should be a future problem. And also the corrective modes can be utilized for higher TC is a future problem. And let me show the collaborators all these. Thank you.